Hello and warm greetings from the United Kingdom. I was just checking and it's about a year since I last left Korea. It seems far longer. I was due to come back earlier in the year, in the spring, but the COVID-19 outbreak just stopped that from happening. I'd like to be able to say that being away from Korea for a year means that I'm forgetting my language skills in Korean, but I never had those in the first place. Sorry. I was beginning to forget the wonderful Korean food, but luckily last week I received a food parcel from Korea and I've had kimchi and nurungi this weekend, so that's been really great. Now the thing I'm missing most is the makgeolli. I'm sure we're all hoping things get back to normal as soon as possible, and hopefully the various vaccines will start to become effective in the new year. I'm certainly looking forward to returning to Korea in time to see the blossoms on the trees. Thank you for inviting me to speak and for coming to listen to this presentation on testing biometric systems and standards. My apologies that I cannot be there in person, but hopefully the extra time spent on recording the talk may make it easier for you to follow my English. And lastly, before I start the talk, as it's already December, I wanted to wish you all a festive Christmas and hope you enjoy the New Year celebrations with your families. Please enjoy the talk. I'll first cover who develops biometric standards and then describe the resultant framework of standards used to support the testing of biometric systems. Next, I will provide details of the core series of biometrics testing standards and show how they support the three unique levels of evaluation performed when testing biometric systems. Following on from these mainstream generic standards, I will show three quite different examples of biometric testing standards. First, we will see an application-specific standard for testing on-card biometrics. Next, an interoperability testing standard used to determine the ability of biometric components from different providers to successfully work together. And third, a conformance testing standard for checking that a biometric component produces outputs that conform to standard biometric interchange formats. Finally, I will show how the ISO Software Testing Standards Working Group are developing an ISO technical report to help software testers using the ISO 29119 series of software testing standards when they are asked to test biometric systems. For this talk, I'm going to concentrate on the biometric standards produced as part of the Joint Technical Committee set up by ISO and IEC. There are other standards bodies that produce biometric standards, such as the International Civil Aviation Organization, which specifies passport standards. But in most cases, the most important standards, as with passports, are adopted as joint ISO-IEC standards. Working as part of JTC1 are many subcommittees, each covering a specific area for standardization. And each of these subcommittees typically includes several working groups. On the left of the slide in blue, you can see that Working Group 26 are responsible for software testing as part of SC7. I'm convener of this working group. SC37 is the biometric subcommittee, and Working Group 5 is responsible for biometric testing. Two other subcommittees are shown as they either develop standards that include security testing of biometric systems or define formats for cards that contain biometric systems. Since its creation in 2002, SC37 on biometrics has published 131 standards, with 29 currently under development. 29 national standards bodies participate in SC37, including CATS for Korea, and there are a further 19 observing countries. This slide shows the interrelation of the 7 main biometric-related areas of standardization. Biometric data represents the core component of biometric interoperability. This data will probably comply with the old biometric data interchange format of ISO IEC 19794, but in the future will comply with the new ISO IEC 39794 for extensible biometric data interchange records, which is replacing it. Biometric formats frameworks, such as ISO IEC 19785, can be used and serve as a wrapper around biometric data. Since biometric data are sensitive data and subject to attack, cryptographic protection is required in interchange environments. Biometric system properties cover domain-specific profiles, security evaluation, and performance evaluation. This is the area we are most interested in, as this is the area where the biometric testing standards for performance evaluation sit. Biometric interfaces are essential to facilitate integration and the use of biometric components. The harmonized vocabulary is used for describing the whole range of biometric technology. Finally, the deployment of applications using biometric verification or identification takes place within the context of societal and cross-jurisdictional requirements. As we saw earlier, Working Group 5 is responsible for testing standards in SC37. There are several ways to classify the biometric testing standards, but here we will group them into four main categories. On the left, in green, are those standards that provide guidance on how to perform specific types of evaluation, such as how to take account of the environmental factors or user interactions when measuring system performance, or how to measure the difficulty of a fingerprint database used for evaluating biometric performance. At the top on the right is a standard that seems a bit out of place, as it provides guidance on specification of biometric systems requirements rather than testing. Below that, in the yellow box, are standards that provide guidance on testing biometrics in specific application areas, such as in forensics or on mobile devices. Last, and most important, we can see the ISO IEC 19795 series of standards around the outside, providing the fundamental framework for all the other biometric testing and reporting standards. We will see how important this series of standards are to the other standards in a couple of slides. Part 1 of ISO IEC 19795 provides the principles and framework for biometric performance testing and reporting. This standard was first published in 2006, but a new version is due to be published early next year. It provides generic guidance on testing biometric systems, and this guidance is applicable no matter whether fingerprints, voice, faces, or whatever biometric characteristics are being used, and it also applies at all three evaluation levels, which we will compare later. One of the most important clauses in this standard defines the fundamental performance metrics used for both verification and identification in biometric systems. On this slide, most of the standards related to biometric testing are shown as connected nodes. The arrows between the nodes show the cross-references between the different standards, and the size of the nodes increases to show those standards which are referenced most often by other standards. As you can see, Part 1 of ISO IEC 19795, the core standard that we considered on the previous slide, is clearly the largest, being referenced from 22 other standards, while the average is less than 2 references. Standards in the same series are shaded in the same colour, so you can see that the 19795 framework standards are coloured in yellow. The standards for conformance testing are shown in purple, Security evaluation standards are shown in orange, and biometric profiles are shown in blue. Standards that do not appear here as part of a series are shown in white. The importance of the core 19795 series of standards can be clearly seen. Next, we will look at the 3 evaluation levels used for testing biometric systems and how these are supported by these framework standards. Here we can see the Common V lifecycle model, showing development stages on the left and corresponding test levels on the right. As you will be aware, the testing of biometric systems has its own unique 3 levels of evaluation. Here we will show how these 3 levels of evaluation map to this lifecycle. At the lowest level is technology evaluation, which corresponds to component testing. Technology evaluation is focused on functionally testing the biometric components based on feeding them biometric test data from test databases rather than from real people. Covering both integration testing and system testing is scenario evaluation. This level of evaluation uses real sensors and real people to provide a far more realistic level of testing. The specifics of both technology and scenario evaluation are defined in Part 2 of the 19795 series of standards. Operational evaluation includes both operational trials and performance monitoring of an operational system, and is, unsurprisingly, normally performed on an operational system with real subjects rather than hired test subjects. Part 6 of 19795 provides specific guidance on operational evaluation. We will now look at each of these evaluation levels in more detail so we can see the main differences. On this slide, the evaluation components are shown in purple. Technology evaluation involves testing driven by test datasets, known as a sample corpus, rather than biometrics from real people. This can be seen by the databases feeding the test drivers on the left-hand side of the figure. The use of test datasets allows the testing performed as part of technology evaluation to be reproducible, which is very useful when this level of evaluation is used to compare competing implementations from different suppliers. The enrollment part of the system is at the top of the screen and is indicated by green components. Successful enrollment should result in a biometric template being stored in the yellow biometric template repository. The blue components are used for recognition, either verification or identification, and compare a biometric probe with the templates stored in the repository. We can get 3 basic sets of measures from technology evaluation, which are derived as a result of analysis performed in the 3 purple boxes. At the top, we can measure how well the biometric data was captured and used to enroll a new template. At the bottom, we can get similar measures for extracting a biometric probe from the biometric test data, while on the right, we can measure overall biometric performance in terms of the false match and false non-match rates. With scenario evaluation, the main difference is that now we discard the test datasets and instead gather biometric data from real people through real sensors. Of course, the level of reproducibility now goes down, as it is difficult to control how real people, even paid test subjects, will present their biometric characteristics to the sensors. However, the increased level of realism means that the test results will give a far better indication of how well the system will work in the real world. As we as testers still have control of the test environment, we can normally gather data throughout the system, and can produce similar measures as for technology evaluation. In operational evaluation, we run the tests in the real environment and normally with real people, such as the passengers going through an airport, rather than using paid test subjects. Reproducibility is now extremely low, and it can be difficult to get accurate performance measures, as if the system permits a passenger to be admitted with a bad passport, it is unlikely we will even know about it. We will, however, know when the system incorrectly stops a passenger with the right credentials. There are less purple evaluation boxes now, as it is often difficult to get access to intermediate results in an operational system. Part 7 of 19795 is far more specific than the standards we have looked at so far. It is specifically for testing just the biometric comparison algorithm on smart cards, an example of which is shown at the top of the slide. Testing of this comparison algorithm requires a large number of test transactions to get statistically significant results. It can be very time-consuming to run each test on a real card, as we have to store a new biometric template for each card owner on the card for testing. And many of these smart cards are set up to limit the number of new templates that they can use, requiring the card to be regularly reset to its initial state. To solve this problem and run large numbers of test transactions, this testing is carried out in two stages. The first stage, shown on this slide, involves 50 people acting as test subjects, each providing 2 biometric samples. This allows the comparison algorithm on the card to be tested with 100 genuine and 100 imposter transactions. Although time-consuming, this set of tests in itself does not provide high statistical confidence, even if every test passes. The same 200 tests are then run with the same comparison algorithm, but this time with the algorithm hosted on a test machine rather than on an actual card. These tests are easier to control and far faster to run, and if the test results are identical to those on the card, they verify that running the comparison algorithm on the test machine is truly representative of running it on the card. On the next slide, we will see stage 2 of this testing. You may wonder how the figures of 50 test subjects and 100 genuine and 100 imposter tests were arrived at. Well, according to the standard, the choice of these values are somewhat arbitrary, which appears to mean that the authors guessed at what felt like a good compromise between time and confidence. Anyway, once we have that verification that the results from both test environments are identical, we can move on to stage 2 of the testing. In stage 2, we now run tests only on the test machine, as we are now confident that it is truly representative of comparisons on a real card. And, as it is easy to run tests here, it is possible to run many thousands of tests to provide what are statistically high confidence results. The biometrics industry places much emphasis on providing confidence in the comparison algorithm, which lies at the heart of a biometric system. However, it can be argued that a disproportionate amount of effort is spent on testing the comparison algorithm at the expense of mitigating other risks in a biometric system. Best practice is to use a risk-based approach to testing that will ensure a reasonable balance of test efforts across the complete biometric system. When we test the comparison algorithm, we should also ask how the test results scale up to when it is implemented as part of an operational system. We also need to question the dependence on a test dataset, especially if we allow providers to tune their algorithms based on their test results, which means as testers, we must be careful to control gaming of the tests. On the other hand, as a provider, we ideally want a comparison algorithm that is easy to tune and optimize for different operational scenarios. And we could also test this attribute of an algorithm. Similarly, it would be useful if the algorithm was easy to modify to handle new biometric data interchange formats, and we could also test for that. A final consideration in this list of largely non-functional attributes that we should consider as testers is the ability of the comparison algorithm to work with biometric components from other suppliers. Interoperability is very important, especially if we don't want to get locked into a single supplier. And Part 4 of 19795 covers interoperability testing. This slide shows a high-level view of a typical biometric system with a focus on the biometric system components that are most likely to be replaceable in a system. These replaceable components are shown in blue. Another way to look at it is that the blue components may be provided by different suppliers, and these individually developed components all have to work together in a single system. As an example, we could consider the use of passports for border control. The enrollment sensor used to generate a photograph may be an individual's camera or phone, while template generation, the creation of the passport document, is performed by a government agency. When you present your passport at a border, the authentication sensor will change depending on which country you are entering, and it may also depend on the type of border crossing. Similarly, the comparison component for checking passports is also likely to change from country to country. In theory, each of these interoperable components shown in blue on the previous slide could be provided by a separate supplier, which could lead to the situation shown on this slide where each colour represents a different supplier. Of course, when we want interoperability of components, then there must be an agreed format for communicating biometric information between them, a perfect opportunity for standardization. In the figure, the biometric information is shown in light green and would typically conform to the ISO IEC 19794 series of standards. One standard for each different biometric characteristic. So, for example, Part 4 is for fingerprints and Part 5 is for face image data. Note, however, that this series is now being superseded by the new Extensible Data Interchange Format standard labelled as ISO IEC 39794. Part 4 of ISO 19795 covers interoperability testing to determine whether the components can work together using the agreed interchange format. Testing for interoperability requires different combinations of components to be tested and the resulting biometric performance measures compared. Of course, with 5 replaceable components, the number of possible combinations to be tested can become very large quite quickly. With just 2 suppliers able to provide all 5 components, we end up with 32 possible combinations. It may just be possible to test all these combinations. However, if we move up to 10 suppliers, we end up with 100,000 possible combinations. And if we return to the passport example, there are known now to be over 150 countries issuing e-passports, which, if they each use their own unique biometric components, would generate a ridiculously high number of potential test combinations. Although in practice, we know that the same organisations will be used by many countries for creating their passports and supplying their biometric systems. Returning to the slide showing cross-references between biometric testing standards, we can see that the Interoperability Testing Standard 19795 Part 4 appears to be a popular member of the 19795 Biometric Testing Framework series. Also popular, and highlighted here in purple, are the conformance testing standards. If you are a supplier of biometric components, then conformance is important, as this demonstrates that your component creates outputs in line with the standard biometric data interchange formats. This should make your conformant component more likely to succeed as part of a complete biometric system made up of components from several suppliers. As shown on the slide, there are two basic types of conformance, Type A and Type B. Type A conformance focuses on confirming that your component generates outputs that are correct, while Type B conformance focuses on the ability of a component to use correctly formatted biometric data. The ISO IEC 29109 series of standards are concerned with Type A conformance testing. Within Type A conformance testing, there are three levels. Level 1 is concerned with data format conformance. That is checking that the output biometric data interchange record matches the format defined by the relevant standard. Level 2 is concerned with internal consistency checking in the output record. As such, levels 1 and 2 are syntactic tests and can be performed solely on the output biometric data interchange record without any need to look at the biometric component generating the outputs. Level 3 testing is more rigorous and checks that biometric inputs are transformed into biometric outputs correctly, sometimes even including testing of the input sensor. On this slide, you can clearly see the three test levels for conformance testing, and that as you move from level 1 to level 3, the cost and complexity increases and the results become more useful. At level 1, the mandatory fields that are defined for the biometric data interchange record are simply checked to ensure they exist and that the values in them are in the correct range. For instance, if we are looking at face data, we would check that mouth, nose and eye data was provided. The example on the slide would be flagged as missing nose data. When we move to level 2, different fields are compared to ensure they are consistent. Looking at the example, we can see that the position of one of the eyes is outside the bounds of the face, which means the two fields are clearly inconsistent. While levels 1 and 2 are static testing approaches, at level 3 we are performing dynamic testing as we test the transformation of input records into output records. Examples of before and after the transformation of face image data are shown on the slide. This example demonstrates probably the biggest problem with level 3 conformance testing, and that is a test oracle problem. How do we decide if the transformation was successful or not? Before I finish this talk, I want to update you on the work being done by Working Group 26 on software testing in the area of biometrics. It is clear that biometric systems are becoming increasingly popular, widespread, and are often mission critical. It is also clear that biometric systems have a number of very specific characteristics which make them both challenging and interesting to test. The current SC7 standards on testing biometric systems are very specific and clearly expect a base level of expertise in biometrics. This creates a challenge for a non-biometric software tester who wants to test a biometric system or a system that includes a biometric subsystem. The current biometrics testing standards have a very clear focus on performance measures, but it appears that there is a potential need for covering other non-functional quality characteristics, such as usability, reliability, and response times, to name a few. Finally, the SC7 biometrics testing standards are not explicitly driven by risk, and we see a great benefit in adopting the risk-based testing approach that is core to the ISO 29119 series of standards to biometric systems. This has led to the development of an ISO technical report on the use of the ISO 29119 software testing standards for testing biometric systems. This technical report will provide an introduction to biometrics for software testers who are new to this area. It will also provide an introduction to software testing for biometric specialists who need to test a biometric system beyond the functional performance metrics covered by the SC7 biometrics testing standards. It describes all the SC37, SC27 and SC17 standards related to testing biometric systems and provides mappings from the most important SC37 testing standards to the ISO 29119 series of software testing standards. For anyone who wants to comply with ISO 29119 when testing a biometric system, so therefore using a risk-based testing approach, it also provides a checklist of risks and corresponding treatments that could be used to generate a test strategy for a biometric system. Finally, it would also provide a full set of test documentation for an example airport biometric system. In conclusion, I have presented a view of the SC37 biometrics testing standards from the perspective not of a biometric specialist, but from the perspective of a software testing specialist. I've attempted to give an overview of the available biometrics testing standards, looked in some detail at the core standards, and provided some insights into example biometric testing standards for on-card biometrics, interoperability testing, and conformance testing. From the perspective of the convener of the ISO Software Testing Working Group, our next steps in this area will be to try and bridge the gap between biometrics testing standards and the ISO 29119 series of standards on software testing by providing guidance on how to apply risk-based testing in conformance with the ISO 29119 series of standards to the testing of complete biometric systems and not just biometric components. Many thanks for listening to this talk, and many thanks for inviting me to talk, and my apologies again for not being able to be there in person. I hope you enjoy the rest of the day.